Hello and welcome. I am Dr. Pauline Fu. In this video, we will discuss numerically summarizing data. Topic includes measure central tendency, measure dispersion, locate position of the data, and finally, we will cover 5 number summary and box plot. So first, we'll talk about central tendency. And I'm going to give you a formula and examples to illustrate. Suppose x1, x2, xn are n observations of a variable from a population. The mean, we use mu, is you add all the number together divided by population size. So this is the population mean mu. If the data is about sample, you need to calculate sample mean. We use x bar represent sample mean. So again, you add all the data in the sample divided by sample size. Notice the difference in notation. For population size, we use capital N. Sample size, we use small letter n. And population mean, we use mu. Sample mean, x bar. Okay. Mean is a method to measure central tendency. Another method to measure central tendency is the median. Okay, I'm going to use this example to do both mean and median. The following data represent the travel times to work for all 7 employees of a startup web development company. So those are the travel time for 7 people. The question asks you to determine the mean, determine the median. So usually you have small numbers, and if not specified, most often the data given is a sample. So we are going to use the sample mean x bar. So we have 7 numbers. You add all the 7 numbers together, okay? So until the last number, and divided by sample size. Okay. So add all these numbers together. Okay. Divided by 7. Okay. I don't have answer, but I can quickly figure out. So we want to do maybe our 23, 36, 23, 18, 5, 26, 43. We want to do the average. The mean is actually average. Okay, so I'm just going to quickly use Excel to get the answer. The answer is 24.86. Okay, 24.86. This is the mean. Okay. Next, let's figure out median. Okay. Median is the number such that half of the data smaller than this number, half of the data greater than this number. In order to find median, first step, you need to sort original data in either ascending order or descending order. Okay. So let's say we arrange original data in ascending order. Okay. So you get 23, no, 5. 5 is the smallest number. 5, then 8, let's redo it. To sort original data in ascending order. So number 5, 18, 23, 23 again, and then 26, 26, 36, 26, 36, and then 43, okay? Median is the number sitting in the middle. So this number sitting in the middle, median is 23, okay? Median equal to 23. In case you have 8 numbers, there are 2 numbers sitting in the middle. You take the average of those 2 numbers. The result is a median. Of course, you have to sort the original data in ascending order, okay? So this diagram shows the relationship between mean, median, and distribution shape. Normally, we have 3 different distribution shapes: skewed to left, bell-shaped symmetry, skewed to the right. If you have a bell-shaped symmetry, mean and median is the same. Mean equal to median. If you have a skewed to the left, mean smaller than median. Mean smaller than median. And if the distribution is skewed to right, mean is greater than median. See, this one is greater than this one because this is 0 from here. Mean greater than median. So this is mean, this is median. Mean greater than median. So far we talked central tendency. Usually you use the mean or median to describe central tendency. There is actually another technique, use the mode, M-O-O-D mode. The most frequently occurred number. Okay. But most often we just use mean and median. Next, let's talk about dispersion. Dispersion is actually the variation of the data. How varied of the data? Are data spread all over the place or data concentrated? But we use the term dispersion. There are several techniques. The first technique is use range to describe the data spread, okay? The definition of range, largest data value minus smallest data value. So for example, what is the range for this data? What is the range R? The largest value is 43. The smallest value is 5. So it is 38 is the range. Beside range, commonly used dispersion is standard deviation. For population standard deviation, we use this symbol, sigma. Sigma. Okay, how do you calculate sigma for population? You use the first observation minus population mean squared. Add the second number minus population mean squared. And you do this for all the numbers in population. Then divided by population size and then take square root. Okay, so this is the standard deviation for population. Suppose this 7 data is your population, just suppose. And how do you calculate the standard deviation? So first step, you need to calculate mu, okay, mu. Mu is the average of the data. Because it is population, we use mu, we do not use X bar. In this case, the population mean is the same as the sample mean because the formula is the same, add all number divided by size, okay? So let's quickly use Excel. This mean is here, 24.86. To maintain accuracy, maybe I need to keep 4 decimal places. So 24.8571. 8571. So this is mu, okay? Once you get this mu, you use each number. So the first number x1 is 23. So 23 minus mu square plus 36 minus mu square plus 23 minus mu square plus last number 43 minus mu square divided by 7, take square root. Okay, so the result would be, I'm going to do it here. It is a standard deviation. Okay, as equal. Any formula in Excel start with equal sign. STDEV dot P means population. Dot S means sample. So we consider this 7 data is population, okay? So what is the standard deviation? And the result 11.3569. 11.6539. So this is suppose it is a population for those 7 data, okay? Standard deviation. Make sure you verify this answer manually. Okay, each number minus mu, square it, add them all, divided by 7, the result takes square root. Can you get 11.6539? All right. So that is the population standard deviation. This is another formula, same result. Next formula is sample standard deviation. We use small letter s. It is similar to population standard deviation, except when you add all the square here, square plus square plus square, you divide it by sample size minus 1. Okay, sample size minus 1. So let's redo the standard deviation if the given data is a sample. So again, we need to calculate X bar. Okay. X bar we already calculated. Oops, it is raining. I got to run home. Okay, one moment. Right, I have this little place here. All right, my goodness. Sorry, it is raining. I changed the location I'm in my gazebo. Okay, some water. All right, so where we are calculating standard deviation for sample. So we know the sample mean 24 point, here we use this 24.8571. Okay. 24.8571. And you use this sample mean, subtract from each original number, square it, add them all, divided by n-1, divided by 6, not 7, and then take square root. And the result of this number, I will use Excel. So equal stdev dot s means sample. And this 7 number. The result is 12.2668. Why this standard deviation is bigger than this number here, 11.65, because you divided by 6, not 7 here. n-1 equal to 6. Okay, so this is how you calculate the standard deviation, sum the score. All right. So far in dispersion, we talked about the range, maximum minus minimum, and we talked about standard deviation. And next, we introduce empirical rule to describe data. Okay. Empirical rule said, by the way, this is suppose data is a normal distributed, bell-shaped symmetry, and this is the mean. Okay. So sigma, this is within one standard deviation. How much data within one standard deviation? Empirical rule said 60% of the data within one standard deviation. And from here to here, two standard deviation. Empirical rule said 95% of the data. Oops, I'm going to move my position. 95% within two standard deviation. And the 3 standard deviation is here. 3 standard deviation. Empirical rule said 99.9% 3 standard deviation. So let's take a look at this example. Using empirical rule, the following data represent the serum HDL cholesterol of the 54 female patients of our family doctor. Okay, so 54 female patients. The question asks you compute the population mean and the standard deviation. Okay, so you just punching those numbers into your calculator or into Excel. Population mean, you just use average, equal average, and select all the data. And population standard deviation, you select stdev dot p. You get population standard deviation. Okay, so the first question, easy job. The answer is here. Population mean 57.4. Population standard deviation 11.8. Okay. The second question, draw a histogram and to verify the data is bell-shaped. Histogram. Okay, again, if you use Excel, you count in those 54 data. Continue 54 data. And then you go to data screening, and then data analysis. You have histogram, okay? You can produce histogram. And if you are using Office 365, you have insert graph. You can also produce the histogram, okay? So anyway, you produce histogram using technology, okay? So the result is this one here. This is the result of histogram. Looks like it is a bell shape. So this is question 2. Question 3. Question 3. Determine the percentage of all patients that have serum HDL within 3 standard deviations of the mean, according to empirical rule. So remember, empirical rule said how much percentage within 3 standard deviations? It is said 99.7% within 3 standard deviations. So question 6. 99% of all patients within 3 standard deviations. And question D. Determine the percentage of all patients that have serum HDL between 34 and 59.1 according to empirical rule. So how much percent of the patients between 34 and 59.1? Yeah, we use empirical rule. So this 13.5% plus 34% plus 34%. And those are all 81.5% of patients will have between 34 and 59. So that is the application of empirical rule. Besides empirical rule, we also have chop-shop inequality. Chop-shop inequality said for any data set or distribution, at least 1 minus 1 over chi squared times 100% of the observation within chi standard deviation. So if chi equal to 2, if chi equal to 2 standard deviation, how much percentage within 2 standard deviation based on chop-shop's inequality? The answer is 1 minus 1 over chi squared, 2 squared, equal to 1 minus 1 over 4, equal to 3 over 4, equal to 0.75 or 75%. 75% within 2 standard deviations. If chi equal to 3, you can use similar method to figure out. Okay. That is a chop-shop inequality. Let's take an example. How do we apply chop-shop theorem? Use chop-shop theorem, determine the percentage of patients. The data is here, 54. This is use this data, okay? Use 54 patients, this data. And this example asks you to use chop-shop theorem, determine the percentage of patients that have serum HDL within 3 standard deviation. 3 standard deviation means K equal to 3. And you plug in 1 minus 1 over K squared equal to 88.9%. Okay. So 88.9% within 3 standard deviation. Question B, determine the actual percentage of patients that have serum HDL between 34 and 80.8. The actual percentage, you have to go back to count how many data between 34 and 80.8. The result is 52. Okay, 52 data between 34 and 80.8. Total number of data is 54. You do division and you get 96%. So that is the Chebyshev theorem. So next topic is about measure of position and outliers. We are going to introduce a new terminology, Z-score. Z-score. This score represents the distance that the data value is from the mean in terms of number of standard deviation. Okay. If you have a bigger Z-score, that means data far away from the mean. If you have a smaller Z-score, data is close to the mean. Okay. And how do we calculate the Z-score? We use formula. If the Z-score is for population, we use data minus population mean mu divided by population standard deviation. If you are calculating the Z-score for sample, you minus sample mean X bar divided by sample standard deviation. The Z-score does not have unit. Z-score always have mean 0, standard deviation 1. The distribution of Z-score is bell-shaped symmetry. Mu is 0. Standard deviation is 1. So let's take a look at example. How do we use the Z-score and make a conclusion about some situation? The mean height of males 20 years or older. Okay, this is male. The mean height is 69.1 inches with a standard deviation 2.8 inch. And the mean height for female is 63.7 inch with standard deviation 2.7 inches. Data is based on information obtained from National Health and Examination Survey. The question is, who is relatively taller? All right, so to do this, we are going to pick 2 people. So we pick Kevin. Kevin's height is, I'll try to use, I use red represent male. So Kevin's height is 83 inches. And then we pick a female, Candice. Candice's height is 76. Okay. And the question asks you, who is taller between Kevin and Candice? Okay. So we need to do the Z-score calculation. For Kevin, we need to use Kevin's height, 83, minus the mean value for male is 69, and divided by standard deviation 2.8. So the Z-score for Kevin is 4.96. Okay. Next, let's do calculation for Candice. Candice is a female. Her height is 76 minus female average height 63.7 divided by standard deviation for female 2.7. And you get the Z-score for Candice 4.56. Woohoo! The rain stops. The sun breaks. So who is taller? Kevin is taller. Okay, Kevin is taller. That is the Z-score. We have another measure to measure the relative position of a data in a data set. That is case percentile. We use capital P, then subscript K. Okay. For example, P1, okay, means one's first percentile. Okay. What does it mean? It means 1% of the data is lower than this number. 1% of the data lower than P1. So now let's interpret this P2 means second percentile. Second percentile means 2% of the data lower than this number. Okay. So this P98 means 98th percentile. 98% of the data lower than this number. P99, 99% of the data lower than this number. So that is the meaning of percentile. Okay. And you can interpret the other way. For example, we say P1 represents 1% lower than this number. If 1% lower than this number, it is equivalent to say 99% higher than this number. Same thing, okay? So let's do P2. P2 means 2% of the population data lower than this number. If 2% is lower than this number, that means 98% is higher than this number. Okay. So similarly, P98 means 98% lower than this number. It is the same as 2% higher than this number. Lastly, P99, 99% is lower than this number, or 1% is higher than this number. Okay. So that is the 10th case percentile, measure the position of the data. So this diagram introduces, actually this is the quartiles. In case percentile, there are 3 important percentile. One is P25, means 25% lower than this number, or 75% higher than this number. The other is P50, means 50% lower than this data, or 50 greater than this data. And we also have P75. P75 means 75% lower than this data, or 25% higher than this data. And these 3 special percentile, we give it special name. We call this is Q1, first quartile. P50 is Q2, second quartile, and P75, Q3, third quartile. And this is this. So Q1 is the same as P, 25. Q2 is actually the median because half of the data smaller than this one, half of the data greater than this one. And Q3 is P 75, 75th percentile. Okay. And also you have smallest data, largest data. So in this diagram, we can see there are five important numbers. The smallest number, largest number, Q1, Q2, Q3. Okay. It's raining again. These five numbers can describe basic characteristics of any data set. Okay. So let's take a look at this example. A group of Brigham Young University, Idaho students. Those students are Matthew, Harry, Nathan, Spencer, Mark Walker, and Mark Skinner. Collected data on the speed of vehicles traveling through a construction zone on a state highway, where the posted speed was 25 miles per hour. The recorded speed of 14 randomly selected vehicles is given below. So this is real life. There are many background noise. Sorry. So those data is the speed of the vehicles when they're traveling through a construction zone. The question asks you found and interpret the quartiles. Okay, quartiles means found Q1, Q2, Q3. Okay. So how do we find Q1, Q2, Q3? You can use Excel. Okay. For example, you enter the data. There are many data. I will maybe just use this data here, or I can quickly jump typing those data. Okay, to find 27, 28, 29, 30, 32, 33, 34, 36, 38, 39, 40, and 40. Okay, so you are asked to calculate what is the Q1, what is the Q2, and what is the Q3. Those are the quartiles. Okay, so you can just type in QU quartile. Okay, so array means this is the data, original data, and then typing number 1 means first quartile. Oops. This is first quartile, and second quartile. QU, okay, quartile. Select the data range. Typing number 2 represents second quartile. Okay. And third quartile. Select data range. Typing number 3, third quartile. Okay, so you got those Q1, Q2, Q3. I'm just going to copy and paste here. Okay, Q1, Q2, Q3. I will also may want to copy the Excel formula so that later on you can practice on your Excel. So I'm going to view. New formula. Where is my formula? Da, 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 da. U. Formula of U. So I can maybe just copy this one, Control C. This is the formula I type in to calculate the quartile, okay? Change this number 1, you get 2, okay? So that is the quartiles, okay? Now we introduce another important concept, IQR, interquartile range. By definition, Q3 minus Q1 is the interquartile range. Okay. So for this one, what is interquartile range equal to Q3 minus Q1 equal to 10. Okay. So equal to 10.5, okay, or 10. And how do you interpret this IQR 10? So the interpretation is the average range for middle 50%. Actually, Q3 minus Q1 represent the middle 50%. Q3 minus Q1 represent the middle 50%. Okay. So the range of the middle 50% of the speed is 10 miles per hour. All right, so that is the quartiles. Next, we introduce the fans. The purpose to introduce the fans is we want to identify outliers. Outliers are data either extremely small or extremely large. So what is the logger fans? Logger fans use Q1 minus 1.5 IQR, you get logger fans. This is continue use the data we use here. Continue use this data, okay, for logger fans, upper fans. Q1. Upper fans, Q3 plus 1.5 IQR, you get upper fans. Once you have logger fans, upper fans, you go to original data. Do you have data lower than 13? Let's check. Do you have data lower than 13? No. Okay. And then, do you have data greater than 53? Go back to the data. Do you have data here? 50 than 53, greater than 53? No. That means we do not have outliers. Okay, so those fans are criteria to locate outliers. Last concept in this video, 5-number summary. Okay, remember I told you before there are 5 important numbers in any data set. You need to identify those 5 numbers: minimum, maximum, first quartile. By the way, second quartile, also called median, and third quartile. Those are 5 important numbers. And based on these 5 important numbers, we can construct box plot like this. Okay, so box plot, okay. Maybe I will go back to here. So let's do the box plot for this, this question here, okay? So what is the minimum value in original data? The minimum value is 20, okay? So you locate, this is the minimum number, 20, okay? MIN is 20. maximum number is 40. Okay, so this is the maximum number 40. And you also need to identify Q1, Q2, Q3. So Q1 is 28, 27.75. You can see it is 28. So that is Q1. Okay. Median 32.5. Suppose this is median Q2. And Q3 38. Maybe here Q3. Okay. So the box plot, you draw vertical line for Q1 and Q3, and then make a rectangular. Also draw vertical line for Q2 and connect this one here. And this diagram is the box plot. Okay, and this box plot can describe the distribution of the data. How? So if you go back here, so these are the box plot. If the median is sitting in the middle of the box, you have bell-shaped symmetry. If this median is close to Q1, you have a skewed to right distribution. And if this median is close to Q3, you have skewed to left distribution. Okay. That's all for this video. Okay. So in summary, what we learned in this video, we did central tendency. We calculate the mean, median, mode. And we also measures of dispersion. We calculate standard deviation for population, standard deviation for sample. We also use range, okay? And then we calculate the measure the positions. We introduce the quartile, Q1, Q2, Q3, and outliers. We build two fans, okay, to identify outliers. Finally, we use a 5-number summary to describe and summarize the data. Okay, that's all for this video. Thanks for watching. See you next time.